Okay, welcome to the eighth class. You guys did very well. Just north of you. Oh my gosh, I'm so sorry. You know, I'm sorry, but Texas had it coming. I don't mean to be rude, but they decided years ago to have their own power grid that wouldn't connect everybody else. And they decided 10 years ago, after a massive ice storm, not to weatherize their power structure. So it was a very predictable problem. Are we responsible for knowing all the parts on different telescopes? It's like knowing exactly what cassegrain focuses and things like that. No, you are not, Micah. You are responsible for refractor and reflector and the differences between those, but the different types of reflecting, no. Okay, so let's get started. Share screen. Wow. No, let's not do that. So, window. Okay. So this is going to be a very intense lecture. I'll be covering a lot of material. Um, and Peyton, I'm sorry about your situation. I don't mean to belittle it, and I it's just it must be so frustrating to be in Texas where 10 years ago they predicted this exact scenario and it happened exactly. And they issued not new laws but guidelines for, well, maybe you should weatherize. So anyway, here, Lecture 8, electromagnetic radiation. This is going to be very dense and very important because we'll be talking about electromagnetic radiation for the rest of the course. First of all, let's start with a movie trailer. So that's 2 hours from now. So make sure to um, check that out. Either go to YouTube and search for Perseverance Landing Live or just go to the NASA website that was listed. Um, Electromagnetic radiations, which we're covering today. Hold on a second. We've got a lot of props and a lot of simulations, so we'll be going fairly quickly. These are the equations that we're covering today, waves and photons, the wave equation. These are very important equations. Again, you're not going to have to do the calculations, but you're definitely going to need to know these equations because I'll ask if the frequency doubles, what happens to the wavelength, and things like that. And we'll be covering resolution. We'll cover this today, but we'll also be covering these in future lectures. So what is light? So until 2015, everything we knew about the universe came from electromagnetic radiation, which sometimes we call light, even though that's kind of a misnomer. We'll talk about that in just a second. So light is a disturbance in the force. It's disturbance. It's an electromagnetic disturbance, and it's a series of waves, just like water waves, except it's a different kind of wave.
A wave is a disturbance which travels from one place to another, carrying energy, but without carrying material along with it. Many waves have a characteristic speed. The size and shape of the disturbance does not affect how fast it travels. This allows us to talk about the speed of sound, or the speed of light. The amplitude of a wave is how far from equilibrium it extends. Harmonic waves, or sine waves, form a regular repeating pattern. The frequency of a harmonic wave corresponds to how many times each second a particular spot goes through its repeating cycle of motion.
So frequency is
The
cycles per
corresponding
second.
wavelength is the distance over which the pattern repeats.
Wavelength is the distance?
The distance for the repeating pattern in space and the time for each cycle are related to each other through the wave velocity. The time it takes one full wavelength of the wave to pass a given point is the same as the time it takes that one point to go through one full cycle of its motion. Thus, for each harmonic wave, the product of the wavelength and the wave's frequency must be equal to the wave velocity. So a wave with longer wavelength must have a lower frequency.
If moving at the same velocity.
Shorter wavelengths have higher frequencies.
So Matthew, it's just per unit time. So here they're using, unit time of say a second. So in astronomy, we always talk about cycles per second. So here it is, wavelength. Now here in astronomy, we often use mu instead of f for the frequency. So the wavelength times the frequency equals the velocity of the wave. Well, all electromagnetic radiation travels at the same speed. We call it the speed of light, although it's really the speed of electromagnetic radiation. We don't call it that because there's too many words, but the speed of light is designated with c. Okay. So let me bring up a couple of simulations. Stop share, start share. And here is electromagnetic radiation. What electromagnetic radiation is you're all familiar with magnetic fields. You got two magnets and there's a force between them that goes through space and you can't see it. There's also electric fields. It's electricity, and that it's the force that takes electrons and puts it through the wires and turns on your cell phone. Well, it turns out that an oscillating electric field will create a magnetic field, and an oscillating magnetic field will create an electric field. And so what you're seeing here is an oscillating electric field creating a magnetic field, which is the blue, and the oscillating magnetic field creates the electric field. And so those two waves will, there we go. Those two waves kind of create each other and they go through naked space, completely independent of whatever created them in the first place. And so we call electromagnetic radiation, you also hear the term photons, which are little particles of these electromagnetic waves. And I can create a photon here on Earth by shining my flashlight, and that photon will then continue, as long as it doesn't hit anything, for billions and billions of years, just traveling across the galaxy, traveling across the universe until something stops it. So once you've created a photon, it's forever. Okay. So let's stop that. On this other one, similar program. This is of a single wave, but it shows you the corresponding wavelength there. Okay. Now, we're not going to, in this course, we're not going to get into the mathematics of electromagnetic radiation. What you do need to know is frequencies, wavelengths, and the fact that these disturbances all travel at the speed of light. So, stop that. So, we can't, science, you're taught in elementary school science. Is that your code? Yeah, so that was done using a programming language called VPython, which is an extension of Python. And actually, yeah, I didn't write the original one, but I've certainly modified the code over time. It's a really, I mean, if you're interested, um, it's not that hard. It's a really nice, it's you saw a very complicated situation. I'm sorry, I'm nerding out here. Let's go back. Yeah, PY. So anybody that's taken PY 205 or 208 is intimately familiar with VPython. Actually, these days they call it GlowScript. That's one and the same. So we can't perform experiments with stars and galaxies. I mention that because in grade school, you were all taught that science exists of people have a hypothesis, they perform an experiment, they observe the results, and they confirm or deny the hypothesis. Yeah, that's the way you're taught. That's not the way astronomy works because we can't very well perform experiments on stars and galaxies. And so the only way, and so astronomy is kind of like archaeology. It's an observational science. We have to just observe what happens. We can't perform experiments. Um, and until 2015, the only way we could observe the universe is through these electromagnetic disturbances. And there's all different types. Yeah, Python, I would agree, Anna. Although I got to tell you, I've started a couple of software companies. The second company I started, our main product was a Fortran compiler. And I cut my teeth on Fortran back in the 70s and 80s. Uh, so, um, yeah, yeah, okay. Let's not go down this rabbit hole. So electromagnetic radiation consists of a whole different types, and we're going to go over these types now. And so, again, you often hear the term photon or the term wave, electromagnetic wave. Sometimes we think of electromagnetic radiation as particles. Sometimes we think of it as waves. We're not going to get into that. Just for the purposes of this course, those are synonyms. And of course, everything travels at the speed of light. Everything except us. You should develop software that automatically compiles assignments through Moodle and WebAssign. Interesting that you mentioned that, Travis. I'm sorry, Dr. Webster is actually working on that exact project. So what is light?
Light is a strange thing. It isn't just what we can see. Light can be broken up into different types, and we call the whole family the electromagnetic spectrum. So even when it's dark, light is still all around us. Light can be created by making an electron oscillate. This creates an oscillating magnetic field and an oscillating electric field, which we call an electromagnetic wave or light. We often represent light as a wave. Just like water waves, light has a wavelength, a frequency, and a speed. The different colours of optical light have different wavelengths, and so does the rest of the electromagnetic spectrum. Gamma rays are the most energetic, whereas radio waves have the least energy. Even so, light is the fastest thing in the universe. In a vacuum, all light waves, even radio waves, travel at an incredible speed of 300 million metres per second. The Royal Observatory is overrun with squirrels. They're hard to miss during the day because they reflect visible light from the sun, but at night it's more difficult. However, they do emit infrared light, and if our eyes could detect it, we would be able to see them in the dark. If we pass high-energy X-rays through them, the squirrels look very different. Humankind has invented lots of different instruments to show us what our eyes can't see, like our Great Equatorial Telescope, which captures huge amounts of light and allows us to see objects that are tens of millions of trillions of kilometres away. We can see matter interact with light and change it. The gases in the Earth's atmosphere scatter blue wavelengths of sunlight, giving us blue skies during the day and red skies at sunrise and sunset. We can watch sunlight reflect off planets and the moon. During a lunar eclipse, red sunlight changes direction as it passes through the Earth's atmosphere and reaches the moon. And although visible light from stars can be absorbed by dust in space, we can detect the infrared light, which gets through to see baby stars hiding in nebulae. Light can even appear to stretch out. Since our universe is expanding and galaxies are moving away from each other, the light they emit is stretched to longer wavelengths. We call this redshift. Some galaxies are so far away that their light has shifted and stretched from visible to infrared, so we can no longer see them. Stranger still, the universe has unknown amounts of dark matter and bizarre black holes. So even if we can detect all the different types of light, there are still some things in the universe that will remain invisible to us.
Okay, cute video. I actually really like that video. Anyway, so the universe doesn't speak English, it speaks frequency. I think that's cute. So let's go down the different types of electromagnetic radiation. We'll be talking about these in great depths. Gamma rays are where the wavelength is 10 to the minus 12 meter. So this is really, really small. So since it has a very small wavelength, it has an extremely high frequency. And we'll get into this in a minute. That means it's also extremely energetic. The energy of the electromagnetic radiation is proportional to the frequency of it. So gamma rays are incredibly energetic. If you're hit with gamma rays, you die. X-rays, we're familiar with X-rays. You know for a fact that X-rays are very high in energy because when you get your teeth X-rayed, they leave the room because it's too dangerous for them. Of course, it's not dangerous for us, of course. Um, and so gamma rays and X-rays are what's known as ionizing radiation. In other words, if an electromagnetic photon of gamma ray or X-ray hits you, it has a high chance of ionizing whatever atom it hits. And when that atom gets ionized, it's now charged and it can cause all sorts of damage. And that's why high levels of gamma rays and X-rays will cause cancer, because it makes all your cells go wonka wonka and destroy yourself. I saw a documentary where you get hit with gamma rays, you turn into the Hulk. Yeah, something like that. Okay, and then between X-rays and visible light is what's known as ultraviolet. And ultraviolet, the far reaches of ultraviolet are still ionizing, but ultraviolet is still very dangerous. And it's a good thing that the Earth's atmosphere filters out most of the ultraviolet. This is what causes you to tan, and why, if you stay out into the sun too long, your chances of skin cancer get high. Again, because these are very energetic photons. Then we talk about visible light, and we'll come back to visible light in a bit. And then infrared light. Infrared light is less energetic than visible light. And we'll talk about in future lectures the fact that every object, every solid object, actually every thick object in the universe emits electromagnetic radiation. And when you look at someone, you think that you see, oh, I can see them. You're seeing them through reflected visible light. But if you turn off the lights so they're in a completely dark room, you could still see them. But you wouldn't be able to see them with your eyes, because their eyes are not sensitive to infrared light. What you'd be able to do is you would see them with infrared light, which is lower energy light that's emitted just because that person is hot. Okay. And let me give you a demonstration of that. So let's stop the share. Okay, so you're seeing me on camera 1. Let's turn on camera 2. Okay, there's camera 2. Let's turn on. Okay, now with camera 2, you can see here is my computer setup. Okay, so there is my computer. Nothing unusual about that. There's the monitor, there's mics. Okay, now I'm going to hold up my iPhone, which has an infrared detector attached to it. Notice if I look at the camera, if I look at the computer, it just looks normal. But now if I look at the infrared sensor on my camera, what I see is that center part on the hinge is incredibly hot. And in fact, it's at 120 degrees. You can see that there. Okay. Whereas the top and the bottom are just normal. Okay. And let me shoot a picture of me. This is going to be challenging. Okay. So I have the sensor looking at me, camera is looking at the sensor. Okay. And you can see I'm hot. Okay. My glasses are cool, but I am hot. Okay. And if I measure it, it would be 99 degrees. You've got a fever. Yeah, I guess I better not, because I'm getting my second shot tomorrow. Okay. So that's infrared. We'll be coming back you are hot, yes. Is the radiation emitted from electronic device one of the reasons for visual impairment through the screen? Camille, I'm not sure I understand the question. If you can rephrase that. Oh yeah, thanks, sorry. Forgot to switch back to the camera after I turned it off. Okay, so that was infrared radiation. We're going to go into excruciating detail about that in future lectures, but I just wanted to show you that demonstration. So let's get back to the screen. Oh, when it hurts your eyes. Camille, actually, no. Typically, what you're talking about eye fatigue, that's typically caused by the fact that your eyes are focused close for a very long time. And what focuses your eyes are actually physically muscles, and those muscles get tired. Okay. What's a good place to start learning how to code? Travis, I would say GlowScript is a perfect place. Uh, I'm not familiar with Code Academy, so anyway, we're going to go back to visible light here. So there's gamma rays, X-rays, ultraviolet, infrared, radio waves, which we'll talk about in just a second. And here the wavelength is really short for gamma rays and X-rays. The frequency is high for the gamma rays and it's low for the radio waves. The wavelength is short for gamma rays and very long for radio waves. So here we've got 0.00001 nanometer, 10 to the minus 9. So this is like 10 to the minus 12. Oops. And over here we got 100 meters. And here we got very high energy, very low energy. Notice that visible light is this little tiny sliver right there. Visible light is important to us because that is the electromagnetic radiation that we observe directly with our eyes. And our eyes only observe this very narrow slitted. We can't detect with our eyes anything outside that band. Now, other animals on the earth do detect some of these lights. In fact, I just read an article that snakes have a infrared detector that's built into them. And bees, for example, have ultraviolet detectors. But most of us are in this very narrow band. And there's a reason why, and we'll get into that when we talk about our sun. And our narrow band, where the wavelength goes from 400 nanometer to 700 nanometer, we observe these different wavelengths and different frequencies of light as different colors. So very short wavelength, high energy light we observe as blue, very long wavelength, relatively speaking, lower energy light we observe as red, and then we have the intermediate colors. Okay. So for this very narrow band, color can be used as a way of sensing the wavelength and or frequency of the electromagnetic radiation that you're observing. And now we're past visible light. We're now into the microwave ovens. Again, microwaves are much higher frequency than radio waves, but much lower frequency than visible light. Radio waves we're all familiar with because we all have cell phones. We all listen to the radio. So when you listen to WUNC, actually you guys are mostly in Raleigh, so maybe you don't. WUNC is at 91.5 megahertz. So that's the million oscillations per second, and 91.5 megahertz would be a wavelength of about a meter or so. Okay? And we do observe the universe with radio waves. And so here is the big kahuna. We have radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and then off the screen is going to be gamma rays. And here is the wavelength increasing. I'm sorry, with the wavelength getting shorter and shorter and shorter from 100 meters to 0.1 nanometers in X-rays, and then 0.001 nanometers for gamma rays. And here's the frequency of that wavelength. There's a million, 10 million, 100 million. So WUNC is right in this region here. Okay. And then we go up to infrared, then we go up to visible, and there's visible light. The wavelength times the frequency equals the speed of light. By the way, I sometimes slip and use F instead of mu. So if you see an F, just think mu. Okay. Wavelength times frequency equals the speed of light. And the energy of the electromagnetic radiation is equal to this constant, which you don't need to worry about, times the frequency. So as the frequency goes up, the energy goes up. Is that why the microwave turntable turns so all the food hits the amplitude of the microwaves? Yeah, Travis, that's exactly right. Because the microwaves are bouncing around, and because the wavelengths are relatively long, they're in the centimeter range. That they'll have peaks and valleys, and those peaks and valleys are where, and they'll constructively or destructively interfere with each other, and so you're going to get spots where it's going to be hot, and spots where it's cold, and that's why the turntable moves things around. Very good. Okay, so that was electromagnetic radiation. We got a whole bunch of other topics to cover in 35 minutes. So I want to talk about how we see images. This is something that it's not in the textbook, but I think it's important for people to know. Um, and I'm going to use the example of a cow. I'm using an example of cow because I'm from the Midwest. We have lots of cows. And the question is, how do you form images? Now, uh, the way that we form images with our eye is identical to what we're about to say, but for the purposes of this discussion, we're going to assume that it's a camera sensor that's trying to create a picture of a cow. So you got a cow, and the cow is reflecting electromagnetic radiation. In particular, electromagnetic radiation is being reflected from its ear, and electromagnetic radiation is going to be reflected from its hooves. And what you want to do is take a picture of the cow. You want a representation of the cow on this sensor. So you want the light from the hoof to hit, for example, the top part of the sensor, and the light from the ear to hit the bottom part of the sensor. Okay. Our radio station decided on the James, I don't know. Good question. And then once we have light that hits the sensor, which has a series of devices that sense electromagnetic radiation that's turned into bits, and it's turned into an image. So the question is, how does this happen? So in both image creation and image display, what we're trying to do is we're trying to convert the angles of these electromagnetic radiation waves into images. So we're trying to convert the fact that from the hoof, it comes in at this angle, hits here. We're trying to convert this angle into an image of the hoof, and we're trying to convert that angle into an image of the ear. Okay. And so what do we need to put the electromagnetic radiation in those places? So let's say we didn't have any sort of device. What would happen is the light from the ear would hit every single part of the sensor, and the light from the hoof would hit every part of the sensor. And so what you'd have is just a complete mishmash. You wouldn't have the light from the hoof and only the hoof hitting that part of the sensor, and the light from the ear and only the ear hitting this part of the sensor. It would just be a mess. Okay. So how do we do that? Well, there's four ways. Can anybody think of the four ways that we can get the light from the ear to hit only this part? There are four ways, and three of them show up in nature. The fourth doesn't. So small aperture, Julie, that's exactly correct. And we'll talk about that. That's the next one. A small aperture is also known as camera obscura. For those of you that have ever gone to the North Carolina Science Museum, the North Carolina Museum of Art, they have a camera obscura out in the field there that you can actually go into. We'll talk about that in a minute. Any other ways that we can a lens? That's exactly right. That's number two, and there's two more. So lenses is the way our eye works. It's the way that camera lenses work. Mirrors, that's correct. That's number three. Julie, you've got this perfectly. There's a fourth way, and the fourth way is by far the most common way that light is directed into a sensor on the planet Earth, on the surface of the Earth. There are literally trillions of examples of this, trillions and trillions of them. Positioning, close. Anyway, you'll see when we get there. So the first way is, as Julie mentioned, the camera obscura, which is a pinhole camera. You literally have a pinhole, and the light goes through the pinhole and strikes that. So you're basically blocking out all of the light. And you can see this at the North Carolina Museum of Art. It's out in the sculpture gardens there. You walk into that, and you can and you close the door, and it's really dark, but there's a hole right there at the top of the roof. And on the floor, you can see a representation of the clouds passing overhead. It's really neat. The downside is it's incredibly dim because you're blocking most of the light. You only have that small little hole, and so it's dim. It's very low resolution. Is it ever used in nature? It is, but not very much. So this is a Nautilus, and it has literally a pinhole camera as its eye. So it has uh, it's a very poor eye, but at least it's an eye. Okay. The second way, which is by far the most common way that light is directed in nature, is by using these baffles, by using these individual tubes. This is also known as a compound eye. The advantages over pinholes, you get more photons per eye, not a lot more, but you do get more. And this is used in nature. So virtually every insect uses this. Another reason why insects use compound eye versus lenses is because of the diffraction limit, which we're going to touch on briefly today. So more on compound eyes. There are many subtypes. The advantages, they're very small. I say no optical path. That won't mean anything here until the next few slides. And you get more photons than a pinhole. The disadvantage is very poor resolution. And that's why, flies can't read. It's not because they're stupid. It's just that their eyes aren't good enough to read. And so typically insects are really good at motion and not so good at resolution. So they can't tell the difference between me and my dog, for example. So they have to use other senses such as smell or motion to make that distinction. But both of those sensor types don't supply a lot of photons. So the question is, can we use every piece of light that comes from that cow's ear? And the answer is yes. We need more photons, Captain. We need to gather all of those photons from the air and put it in a particular bucket. And to do that, what we want to do is take all those photons and gather them together and bend them and put them in a place. So that means if we can bend the electromagnetic radiation, we can create an image that uses a lot more photons. And so we do that by bending the light, and we do that with lenses. So in lenses, if you have an incident electromagnetic radiation on something like glass, what it does is it does what's known as refraction. In other words, the speed of light is slower in the glass than it is in the air. And because the wave hits at an angle here, that wave slows down, and as it slows down, it bends. Okay. Uh, and so, anyway, let me show you this video, and then I'll get back to the
Light
bending of
travels
light.
outwards from a source, bounces off of objects in its path, travels into your eye and onto your retina, where it forms an image. If your eye had no lens, light from a single source would hit your retina in lots of places and result in a smeared out mess.
So, Rael,
which is
yes.
exactly what happens when I take the lens
I'll talk
off
about
of my
that in a
camera.
second.
A lens focuses that spread out light, corralling it into a crisp image on your retina. And after a little excitation of light-sensitive nerves and interpretation from your brain, you see. But wait, when we look at an object, the background and foreground are usually blurry, because a lens can only focus light coming from one distance away. If an object is too near or too far, its light will again be spread out on your retina, leaving you with a blur. Fortunately, muscles in our eyes allow us to accommodate by squeezing the lens, which changes its focal length so we can see at different distances, except when we can't, or when our lenses become damaged, in which case we need glasses. Unlike a lens, a pinhole or other small opening can focus light coming from any distance. Because it's such a small opening, it only allows light to come through in one place, and thus in only one direction from any particular source, so there's no blur, and everything is in focus. If you're familiar with photography, this is why using smaller and smaller apertures makes everything in your photo come into focus. Of course, small openings like pinholes and camera apertures create crisp images by blocking rather than focusing light, so the images are much darker, which is a major reason why we use lenses rather than pinholes for glasses, telescopes, and eyes. And yet, in a pinch, looking through a tiny hole made with your fingers can help you see. Now do you see why?
Okay, so Rael says, oh, I thought the speed of light never changes. Yeah, it doesn't, but we talk about it as if it does. So you often say that the speed of light is less in glass. And so when the speed of, when electromagnetic radiation such as light goes down a fiber optic tube, we say the speed of light is 60%. The speed of that light is 60% the speed of light. So both statements are true. The speed of light is always the speed of light. What happens when you're in a material such as glass is that the light hits an atom, it's absorbed, and then it's re-emitted. And that time between absorption and re-emission adds a little delay. But when it goes from atom to atom, it's traveling at the speed of light. And so colloquially, everybody talks about a reduced speed of light. Sorry, I didn't mean to get too confusing here. So let's talk about this refraction lenses, and let's go to, right? Huh, oh, no, that's not it. Okay, so back to this, and you might, here we go. So here's a light beam, and it's hitting glass here, and the light beam consists of a series of fronts, and as the front hits there, the first part of the front is slowed down and it's bent. Okay, and so because this, in this case it's water, has what's known as the index refraction, and the index refraction, if that number is higher, it means the speed of light is slower in that material. Does light gain mass when that happens? Uh, Really, not really, because it's absorbed and re-emitted at the same frequency. And so so what you're saying is, does light gain energy? Because the light itself doesn't have any mass, but it does have energy. Uh, if it's re-emitted and re-emission scatters light, then why can we see through glass and water? Oh my gosh, Trevor, I'm sorry. This will take us down a rabbit hole. So let's just delay that question. I'll answer that later. I actually wrote a whole book on the subject. It's called Number by Colors. It's about human color vision. But for the purposes of this course, uh, all you got to know is that when light hits a material other than a vacuum, it will slow down a little bit depending on the material. And some material will slow down a lot, other material will slow down a little bit. So here we go to glass. And so notice it bends more when it's in glass than when it's with water. Okay. And notice here it comes down and it's refracted, it's bent. And this bending is why you can focus light. You can bend um, different beams of light depending on the angle that it intersects that with. There's also this reflection here, which we'll be talking about in a little bit. So back to, so with a lens that's properly shaped, it's shaped so that light from this beam here is bent a lot as it goes here, and light from this beam here is bent down. So this beam is bent up, this beam is bent down. And so what you do is you shape the lens very precisely so it bends these beams in the exact correct proportion. What is the unit of refractive index? The unit of refractive index is a measure, it's an inverse measure of the speed of light in that. So for instance, 1 over 1.33 would be equal to the speed of light in that medium. Okay. Uh, so if you create this lens properly, then you can focus all the light beams from the cow's foot in one place on there, and all the photons from the cow's ear on one place there. So there's problems with this. And the problem is, as mentioned in the video, you have to focus the light. Okay, so it's not like a pinhole camera. And you have to focus it, and there's only one distance from the lens to the object that you're looking at that is in focus. As you saw when I showed you the camera 2. In fact, we'll show that. Here's camera 2, and note that uh, my hand is out of focus, and the computer is in focus. Okay, let's see if I can get it to go in focus. No, I can't. Okay, so they're different focus So the light can only be focused from a certain distance. There's something called spherical aberration. That's where the shape of the lens isn't perfect. And so different beams at different parts of the cow's ear will focus at different places. And so it doesn't quite form the right place. And then here's the tricky thing is that, and this is the worst thing that lenses have, is that light of different wavelengths or different frequencies. So in our case, different colors have different indexes of refraction. And so they will bend at different angles. And so the colors will come to focus at different parts. Okay. And then there's something known coma and the field curvature and the diffraction limit. So you're going to need to know about chromatic aberration. That will be on the exam. These others are just for your own interest. You will need to know about diffraction limit. Okay. Solutions to these lens problems is you have very unusually shaped lenses, which are expensive. You have multiple lenses. So here is a cutout of a Nikkor f2.8 80 to 200 lens, which costs about $3,000 because it's got 23 different lenses with and they're made of different materials, all of whom are made to cut down on all of these different problems that lenses have. And in fact, here is that exact lens. So this is that is the Nikkor 2.8, sorry, uh, 300 lens. That lens costs more than all my other cameras put together. It's a great lens though. So, and so this brings us to the eye. Does this astigmatism, how does astigmatism affect vision? So our eyes are actually very poor sensors. They have all of these problems that you saw. Uh, the what happens is that the eye uses the brain as a system to trick us into thinking that our eye is a perfect lens. But let me show you a little bit more about the details of the human eye. Let's go to this, how the human eye works. Okay, so here's the human eye. There is the lens, just like your camera lens has, but notice that the sensor plane of the eye isn't a nice flat plane like a camera. It's curved and it's got a very complicated curvature. And so there is uh, the lens of the eye, and there's the muscles which change the shape of that lens, and then the sensor is in the back there. It sucks that we can't take pictures of the night sky as we can see it with the naked eye. You can, you have to have the right camera and the right lens. So, so here is how the images are formed. The light comes in and the lens changes its shape, and then it creates a focal image there on the back of the surface of the eye. And on the back of the eye is what's known as the retina. I'm sorry, the fovea back here, which has all the rods and cones that detect the light. Would it be possible to eliminate the blind spot in the eye with a lens? Um, yes and no. So what Patty is talking about is that there is a blind spot in the eye that doesn't have any sensors. We typically don't notice because our brain, uh, you know, creates a pseudo image so we don't actually see the blind spot. It's kind of tricky how it does that. And so theoretically, I guess you could create a lens that would send all the photons that would be going to the blind spot around to other sensors. But, you know, our eye kind of does that by itself already. So I'm not sure that you'd need to. What causes floaters in your eye? What causes floaters in your eye is little particles in the aqueous humor of your eye. So let's go back to the lecture. So there's the camera, there's the eye, and the eye has three sensors, a red, green, blue sensor, and so it's sensitive to the high, medium, and low wavelengths of light, which gives us our color sensitivity, which many animals don't have. And we also have a fourth system um, called the rod system, which we use, you know, at night, and it's only a black and white vision. You're all familiar with that. Okay, so the fourth thing, what about when you see stars in your eye? Uh, so what causes one to be colorblind? So Roxy, what causes one to be colorblind is we have three different sensors that correspond to red, green, blue, or low, medium, and high wavelength light. And if one or two of those sensors is not operative, then you're colorblind. Most people, the 99% of people that are colorblind are really not colorblind. What they do is they have reduced color sensitivity. They've lost one of those three sensors. And actually, there's a whole chapter in my book on this. So we've only got 15 minutes, so I'll come back to that. What about when you start to see stars in your eye? So Jacob, I don't know, but I can tell you that when astronauts go to the ISS, they see flashes of light almost continuously, you know, a flash every few seconds, and what those flashes of light are is cosmic rays from intergalactic space hitting the aqueous humor in their eye. And so they're seeing those flashes from outer space particles. And we don't see them here on Earth because most of those cosmic rays are absorbed by the Earth's atmosphere. So we talked about three ways to focus light onto an image sensor. All three of those are used in nature. The pinhole camera is used by a couple of Nautilus. Uh, 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 no, they're squid, I guess. Um, compound eyes is used extensively with insects. Lenses are used exclusively by mammals and higher animals because they're very sensitive. They're very, very complicated, but they're very, very powerful. The fourth type of focusing light is using mirrors, which to my knowledge is not used in nature, but is certainly used in technology. So it bends light not by refraction, but by reflection. And it's superior because it doesn't have a lot of these bad things that lenses have. It doesn't have spherical aberration. It most importantly doesn't have chromatic aberration. The reason why is that the refractors, the angle that the light bends depends on the index of refraction, and the index of refraction varies depending on the color of the light. With reflection, angle of incidence equals angle of reflection, independent of the frequency. It's always angle in is equal to angle out. It's a direct thing, and so there's no chromatic aberration. You do need to know this. There's no chromatic aberration in mirrors, and that's one of the most important advantages of mirrors. You only need one surface. You don't need like 23 surfaces in my expensive telephoto lens. You mount it on the back, not on the edges, so you can make these things really big. And so, in fact, all large astronomical telescopes are mirrored, are reflectors. In 2019, there was a flash of light in a black hole. Sophia, we'll be getting into that in the lecture that I give on black holes. The problem is that the image forms in front of the mirror. It forms in front of the mirror where the light is coming in. And so you need some way to move that light off. And here's the classic way to do it. The light hits a mirror, it hits a little smaller mirror, and then it comes off to the eyepiece here. And so the light that would normally come from here is blocked by this smaller mirror. Okay. But that said, they're very, very popular. So let me show you an example of the difference between refractors and reflectors that you will be responsible for. Okay, so here is let's do a refractor. Here's a refractor. Here's the lens. Light comes in, it's bent by the lens, and then it comes in, it's focused in the eyepiece. And then a reflector. The light comes in, it's reflected off of this mirror, and then it's a secondary mirror, and then it's sent down then. Okay. So again, the refractor is typically used for camera lenses and for smaller telescopes. Larger telescopes exclusively are these reflectors. So, and let me show you. Yeah, keep going. So there's another problem with telescopes. So you want to use these things that form images to take pictures of the sky. The problem is the sky moves. The sky is moving continuously around. And so you need some way to keep your telescope pointed at the sky as the sky moves. And so let me show you that. So, and okay, so camera 2, there we go. So here is a small telescope. This is a reflecting telescope. You can tell we can look down center there, and there's a mirror way back in the middle there. In fact, you can see the mirror there. Okay, and typically this telescope is mounted at an angle. Okay, so it's tilted like this. Now the sky is rotating around, and if this axis here is pointed at the North Star, the sky rotates around the North Star. And so if this telescope then rotates around like this, it can follow the motion of the night sky over the time. And if you ever go to a large observatory, you will hear this sound. Now it won't move this fast because the sky doesn't move that fast. But this is it. This part here has to be pointed directly at the North Pole. So where we are it's actually be pointed more like this. Okay, it would be a fairly extreme motion. Okay, so that's an example of a reflector. Let's go back to me. Go back to the presentation. Okay, so that was reflectors and reflectors. And so here, optical telescopes, we've got a refractor, a reflector, and I showed you the difference between those two. And the fact that as the sky moves around, if the fork of the telescope is pointed towards the North Pole, then as the mount rotates, it will keep the same pointing at that celestial sphere as the celestial sphere rotates around. Okay. So you always need some sort of mount to keep the telescope pointed at the right place. Now, typically very expensive telescopes that cost $1 billion, no longer have this inclination. They're mounted flat, and that's because a computer will do these two movements. But for traditional telescopes that have an equatorial mount, all they have to do is rotate around this angle to keep pointed in the same direction. They don't have to do two motions. So here the Earth rotates around, and as the Earth rotates around, the telescope has to point in the same way. Yeah, so Camille, I actually, this is my backup telescope. I actually have a very fancy small telescope that I put it in my, well, not my backyard, but my community yard, turn it on, and it automatically senses where it's pointing, and it automatically locates where it wants to go. So it's really neat. It's more of a computer than a telescope. So we have talked a little bit about diffraction. Diffraction is kind of the whole ballgame when it comes to reflectors and refractors. Yeah, yeah, it was expensive for its size. So the photons, we've talked about photons being waves and particles. Now we're going to talk about, so you can control it remotely. Yeah. So for those of you that are in PY125, you know about controlling telescopes remotely. A cute story. I was in Chile several years ago on the mountain that had a bunch of large astronomical telescopes, and I had a couple hours to kill, so I was just wandering around the mountain, and they had dozens of telescopes mounted on the mountain. And as I was wandering around, one of the telescopes had a University of North Carolina at Chapel Hill sticker on it. That is the exact telescope that you guys use in PY125. So anyway, here is photons are waves, and anytime you get a wave, waves tend to bend, okay? And that bending of the waves is known as diffraction, okay? So when waves go through any sort of obstacle, such as a lens, it will bend a little bit, and that bending a little bit is what smears out images. So this is where the images of two stars will bend and merge together, and the maximum resolution that you can use to see anything depends on the wavelength. So and the resolution in arc seconds. Arc seconds is that angle, and so you want this number to be small. In other words, you want to be able to separate two stars that are separated by, say, 1 arc second or half an arc second. So if I say 1 arc second resolution, what that's saying is that there are two stars that are 1 arc second apart in terms of their angles, and I can see them as two separate stars. If those two stars were 1/10 of an arc second apart, and the resolution of my telescope was only 1 arc second, what I would see is a blob. I wouldn't be able to see them as two separate stars. And so I want this number to be small. And so the resolution depends on the wavelength. So a shorter wavelength means I get better resolution. It also depends on the diameter of the telescope. And so if the diameter is big, then that means I get better resolution. This is why people want bigger telescopes. Bigger is better. In astronomy, bigger is always better. Now, this resolution is uniformly true all the time. For visible light, remember, visible light is a very narrow range of wavelengths. And so for visible light, this really comes down to 0.113 over diameter in meters. So if you have a 1 meter telescope, its resolution will be 0.113 arc seconds. If you have a 1/10 of a meter telescope, which is about the size of my telescope, then the resolution is going to be 0.113 over 0.1 or 1 arc second, which is about what the resolution of my telescope is. Okay. So again, this equation is due to this bending of light caused by this obstacle. And it bends less if the hole through the obstacle is big, which corresponds to the diameter of the telescope. If the diameter of the telescope is small, then the light bends more. And it also depends on this wavelength.
The next thing I want to look at is what happens to a water wave when it passes through an aperture. Well, I've fitted an aperture here, but it's rather too wide for what I need at the moment. So if I fit these sliding doors, I can make an aperture that's about 3 centimeters across. And if you now look at the screen, you can see that as the waves pass through the aperture, they spread out. This spreading out of a wave as it passes through an aperture is known as diffraction, and it's a property of all types of waves. So what do you think controls how much the wave spreads out? Well, one possibility is the width of the aperture. And what do you think would happen if I made the aperture smaller? Well, you might be surprised to learn that a narrower aperture leads to more spreading out of the wave, more diffraction. If instead I make the aperture wider, then after it's settled down, you can see that the wave becomes less spread out. The diffraction is less pronounced. And if I were to make the aperture very wide indeed, then there'd be hardly any diffraction. Well, I'm now going to return the aperture to its original width and take a look at the effect of changing the wavelength of the wave. Now remember, I can change the wavelength by altering the frequency of the paddle using this control here. If I make the wavelength longer, you can see that the waves become more spread out beyond the aperture, more diffraction. And if I make the wavelength smaller again, here's where we started, then even shorter wavelength, then there's less diffraction.
So the resolution improves if the wavelength
So here are the
gets
two separate
shorter,
factors that affect the
higher
diffraction of a
frequency.
wave passing through an aperture. The wave spreads out more if the aperture is made narrower, or if the wavelength of the wave is increased. And conversely, it spreads out less with a wider aperture or a shorter wavelength. In fact, all kinds of waves, not just water waves, exhibit diffraction at an aperture, as long as the aperture is not too big.
So here we've got, oh, sorry. To get better resolution, we want a shorter wavelength and we want a bigger aperture there. Okay, so we want this small and this big because we want the resolution to be as small as possible. And so this is a very complicated chart, and I apologize for that. But here is the resolution. So 0.001 arc seconds, that's good. So 1 arc second is like your typical small telescope. 100 arc seconds would be like an arc minute. This is like the human eye, okay? And here's the visible light beam. So my telescope, if I go up here, and so if I look, ignore all of this because these are different frequencies and this is a little confusing. Just look at this line, which is visible light. So 1 arc second visible light there, that's about an 8-inch telescope. Now that's a 4-inch telescope, but I don't want to get them upset. Okay. So here we go from about a 8-inch telescope in that range. If I wanted to get a 0.1 arc second, I'd have to have a telescope that's 1 meter, 3 feet across. If I want 0.01 arc seconds, I'd have to have a 10-meter telescope, which would cost, a few $100 million. Okay. So, and here is the demonstration of the resolution of the image. This is 1 arc second. This is about, on a good day, what my telescope could take. And this is 10 arc minutes, and you can see how fuzzy that is. So you want a lot of resolution. Notice that as you go to different radio bands, so for 1 arc second here, and you want to take an image of radio bands at 1 arc second resolution, your telescope's going to have to be a kilometer across. So James Webb is on here. In fact, it's right there. There's James Webb right there. James Webb is up here at about, 6-8 meters, and its resolution is about 0.1 arc second. Okay. Now, James Webb is not a visible light telescope. It's an infrared telescope. So it's actually in this region here. Okay. So not only do you want big to get better resolution, you want big because you want more light. Okay. And so the light gathering power is equal to the area, the surface area of the telescope, which is proportional to distance squared. It's like 2 pi r squared. That's just the formula for the area. And here's a picture of the different sizes of telescopes. So here is a tennis court. There's a basketball court to scale. There's a human. Here's the Hubble, which is not particularly big on this scale. Here's the 30-meter telescope that is everybody's protesting about in Hawaii. Here's the Giant Magellan telescope that's still under construction, 2020. That's kind of a joke. Large Synoptic Survey Telescope. This is the telescope that I was at the christening of a few years ago there. And you can see that on the surface there, we're making some really, really big telescopes. Just trying to, and here's the James Webb. So although the Hubble is small compared to these guys, the James Webb is a sizable telescope, okay, if it ever gets up there, okay. Why are they protesting it? They're protesting it because it's on Mauna Kea, and they say Mauna Kea is sacred to them, and don't get me started. Okay, so we can see on the surface of the Earth visible light. Okay, you're all familiar with that. You look up. We can also see radio waves, but we can't see microwaves, most of infrared. We can't see UV, X-rays, or gamma rays at the surface of the Earth. The atmosphere absorbs all of this electromagnetic radiation. And I'm sorry, I'm going a little long today with fewer QAs just because there's so much material, and this is such an important lecture. But trust me, I'll stop before the class ends. Okay. So the atmosphere has a dramatic effect on seeing. So I was saying that you can get down to 0.1 arc second and 0.001 arc second if you have a really big telescope. I lied. You actually can't, because the atmosphere pretty much limits you to what we call seeing of a resolution of about 1 arc second. So my tiny little telescope has the best seeing of any telescope, which is about 1 arc second, because the atmosphere muddles it up so much. There are solutions to this, and one solution is you use a computer to calculate what the atmosphere is doing and create a deformable mirror that deforms thousands of times a second that inverts this turbulence. And you can see the effect there. This is the original 1 arc second image of Saturn. And here it is after they've gone through this adaptive optics. And so the question is, how do they calculate what the atmosphere is doing? They do it by shooting up lasers, hitting the atmosphere, having the laser light reflected back down, and seeing how it distorts that laser beam, which they know for a fact is a point source because they shot it. It's a laser. Okay. This is very expensive, very complicated, but it does enable you to produce very sharp images even with ground-based telescopes. Are there a lot of computer scientists in astronomy? Actually, all astronomers are computer scientists. I don't mean to be flip about that, but we spend all our time writing computer programs, just because the sort of analysis we need to do and the calculations we do are incredibly intense. And I'm going to stop there because I'll come back to space telescopes and radio telescopes, but I got the most important things done. So I'll open it up for questions. Yeah. So, uh, so um, Anna, to give you a concept, I went to a talk where they talked about gravitational lensing, which we're going to talk about in this course. And she talked about how gravitational lensing warped the images of galaxies. And by using that warping of the images of galaxies, you could detect the distribution of dark matter in the universe. And so after the talk, I asked, well, what do these warped images of galaxies look like? And she says, oh, you don't understand. Um, you can't actually see the warping with your eye. Only the computer can see it. In other words, we're no longer observing in astronomy with telescopes. We're observing with the computers. Well, thank you, Maggie. I appreciate that. Telescopes are interesting. By any chance, do you know which computer language are used mainly for this type of stuff? So, Andrew, believe it or not, they're all over the map. So, certainly the control interfaces for astronomy stuff is traditionally Python, just because Python's so easy to code. But the code itself, the deep code that does all the calculations, it's like, you know, high performance software du jour. There's actually some Fortran code, believe it or not, still in use. But most people are using things like C++ and things, whatever they can use that's fast. Um, uh, other questions? Oh, thank you. I appreciate it. And I'm so glad I have power. I can't tell you. Can you explain how the eye work good? Could we have a link? Yeah, let me think about that. I mean, one link is just my textbook, which is the number by colors by me. But I'll see if I can get a link to that. Thank you. Okay. Any other questions? Feel free to turn on your mic if you want. Okay. No more questions. You all have a nice weekend. Stay safe. Don't get frozen. And we'll see you on Tuesday. Thanks so much. Bye bye.